All right, we'll talk about the other problem dealing with continuous variables. Okay, so let's take this example. This graph. This is like y is equal to x squared. Okay, in this example, we had x as an input, y as an output, and it was linear. Okay, which means that like x changes like 1 unit, then 2. I mean like 1 to 2 is again it's all 1 unit. This graph is linear, so y is equal to mx or y is equal to 2x. Okay? This is the equation of this simple multiplication. If you really convert this into this linear equation, this becomes a straight line with slope 2. Okay? Now the slope is always consistent and constant here. Now let's take this example. Okay, this y is equal to x squared. Okay, what it really means is when x is equal to 1, when x is equal to 1, y is equal to 1. This is x, this is y. When x is equal to 2, y becomes 4. When x is equal to 3, y becomes 9. So if you see that for every unit change in x from 1 to 3, 1, 2, 3, the change in y is not constant. Here in this case the change in y was constant. 4 minus 2 is also 2, 6 minus 4 is also 2. If we take one more, 8 into 6 is also 2. The change is constant. The slope is constant. So we are able to find a slope using a simple formula, rise over run. Okay, which means this is run, this is rise. Rise is y-axis, run is x-axis. Every unit for change in x, we have change in y, and the change is constant. That is the reason the slope is constant here. Now here the slope is not constant. Between this 4 and 1 the slope is 3. Between 9 and 4 the slope is 5. Which means the slope is, take any point between 1 and 2, and if we try to find the slope, it is not going to be constant. So there is no one slope for this problem. Okay, and this is how the real world is all about. Okay, nothing is like this in this real world. Okay, nothing, I mean everything in this world is changing. Okay, suppose if you are trying to launch a rocket, the earth is rotating, it is changing its position, the rocket is going in the direction towards the sky, the fuel is changing, the fuel is burning at a rate, the flight is, the rocket is going at a different rate. Okay, and it takes a different path. Okay, there is a lot of changes which happen. Suppose if you wanted to start from Earth and reach in Moon or reach in Mars, imagine things will change. Okay, that is how the real world is. Okay, if you just walk around, nothing is straight. Okay, even if you take the roads are curved. Okay, the roads are curved. Okay, if you put a bridge, the bridge is curved. Okay, and if you talk about any object, our cycle, car. Okay, nothing is having a straight slope. Everything is having changes in all points in time. So most of the real world problems have to be dealt with changes. Okay, so now how do we deal with this change? Okay, now here the idea of dealing with changes is trying to find out a way which we can approximate the slope at every point of time. So let's say here the slope at this point is 0. Slope at this point is negative, which means that the negative slope comes here, becomes 0 and becomes positive slope, and at every point of time the slope changes. So we are trying to find out a way how, by which we can find the slope of this. Okay, now there is a notation in calculus which is called dy, okay, and dx. This is to say that for a small change in x, what is a small change in y? Okay, because we could not say take a value m, because m is usually large, give 1 unit. But in case of this, in case of continuous graphs like this and things change continuously, where things keep changing at every instant of time, so we have to take small changes actually and try to find out what is the change in x, small change in x and small change in y. Now, before we get into this, how to find this, let's visually see what is x squared. Okay, just see what is x squared. Okay, let's take the square of of side length x. Okay, and this is the area of the square is x squared. So which means that this graph, which is y is equal to x squared, can be represented like this. Okay, its area. Now, what we're trying to find out is, for a small change in x, what is the change in y? Okay, in this example. Similarly, for a small change in x, what is the small change in y? Y we can call it as area, which is because y is equal to x squared. So for a small change in x, what is the corresponding change in area? Suppose if I change, if I change the length of x to be like this is the new x, the area changes, right? If you see here, this is the original, this is the original x, and I've increased the area by this. This is like x plus h. Okay, let's call it as h. There is a small change in area. So overall, what has happened is the area has changed. Okay, the area has changed. Now, the area has changed in three points actually. What has happened is the length of this has increased by this portion. The breadth has increased by this portion. Okay, this change. Okay, we call it as dx. Okay, a small change in x. Okay, I'm just making it a little big. Okay, so that we can visualize it. But technically, think that it is a very small change which you cannot even visualize it. Okay, this is dx. Now, let me put it this way. Okay, this is just to visualize. Okay, a small change in x has changed the area x squared. Okay, that's what it really depicts actually. Now let's put it this way. Okay, now this is x. Let's take this as x. Okay, now this portion, and this portion. I'm just trying to break this into three different portions. It will become large. I'm just making it small so that we kind of visualize it when it has a small change, how it looks. So this becomes this when you do x. So this portion is dx, this portion is x. This portion is x, this portion is dx. Which means there is a small change in x in this direction. I'm increasing the x by a small portion, and this is the original length of this square. So I have x is the original length and small portion here. Now, if you see this small box is like dx here and dx here, okay, which means that there's an increase in this. So when I try to kind of make small incremental changes to this square using and if you think that okay, a small change in x, what happens to y? This is what it becomes. So if you see here, let's try to reconstruct our slope. Okay, we are trying to find out what is the small change in y with respect to change in x. Okay, so change in y is what is the change in area with respect to change in x. What is the change in area? This is the original square. We leave it. This is an area x dx. Okay, I'll multiply this x dx. Okay, this is like this becomes a rectangle. Okay, with a small change in dx. As the width, and this is the length. Okay, this becomes x dx as the area of this rectangle. Now let's check what is this rectangle. It's again x dx. This is the width, this is the length, x dx. Now this becomes dx into dx, a small square. It becomes dx square. Okay, so this becomes 2x dx plus dx square. Okay, now we are trying to find the change in area. Okay, so let's keep it this change in area like this. Okay, I'll come back to this where this dx comes from. Now if you see here, if you find the change in area, it becomes x plus dx, 2x dx plus x square dx square. Okay, now what we are trying to say is, for a small change in x, which is like very small, okay, close to 0, what is the corresponding change in the area is what we're trying to find out. So think of it as a very small number. Okay, let's say it's like 0.01. If you square a kind of a very small number like 0.01 or 0.001, it becomes even smaller, right? So it becomes like 0.0001 or something. Okay, it becomes infinitely small for a small change. So this dy becomes 2x dx. This becomes, very small. We can if this changes, we can ignore that. Okay, now if you bring this dx here, dy by dx is equal to 2x. So this is what we learn when we start learning calculus. What is the derivative of x squared? We learn it as 2x. Okay, how does it come from? I mean, you can visualize it as a square. Okay, square is nothing but the area of the square is x square. Okay, area of any square. Okay, is like side length of a is becomes a square. If the side length of b, it becomes b square. Okay, so it is just area of a square. Okay, it's a formula. So similarly, this area of the square increases from x to some x plus dx in all directions. So we're trying to quantify that change in area. Okay, if we try to increase, I mean, if we take x, a small change in x, this becomes dx, and small change in x becomes dx. The overall this length has to maintain. So it's x, and this portion becomes dx squared. So when we approach. We also use the term when the small incremental change when it approaches 0. Okay, what it really means is that if you have I'll give an example and then come here. If you have something like x by x minus 2 or something, okay, when x is equal to 2, there is no solution for this. Okay, it becomes 0, means like 2 by 2 minus 2 becomes 0. Okay, 2 by 2 minus 2 becomes 0 because at x is equal to 0. I mean, x is equal to 2. This problem becomes undefined, or I mean, like if we have 1 by x minus 2, it becomes like at x is equal to 2. This becomes 0. So when we are trying to have problems like this where we don't have solution exactly at the point x, okay, we can approximate it. Okay, rather than having x is I'll write it one more time. The problem is I'm trying to find the problem solution for 1 is equal to 1. Y is equal to 1 by x minus 2. If I put exactly 2 here, it becomes 0. So what I can do is, I can put something very close to 0, like 1.999999 or something, and then I can subtract with 2. Now, this doesn't become 0. Okay, it has a very small value but doesn't become 0. So this is what we call it as limits. When we are not able to find a solution exactly at that particular point, we can find a solution close to that point, okay, and approximate that problem, and still this is sufficient for us to work with in the real world. Okay, even though and it is very close to 2. Okay? And we are not compromising compromising on 2, but we are making it very close to in such a way that still there is a solution for this problem, but we don't have to kind of worry that it becomes 0 and I have no solution. So that is what we are trying to do with this. So when this change is very small, okay, then when we try to multiply it and becomes very small, that becomes very marginal, that it is not having any impact on our original output. Okay, let's say the loss of information between 1.9999 up to infinite precision to 2, the change is very small and we can still live with it. Okay, that's what is approximation. Like that's what we're trying to use calculus to kind of approximate situations where you're not having any I mean like exact solution, which is still close to the real answer. Okay, you will not have much difference between like having a separate between 2 and 1.9. Okay, the difference is still acceptable and we can still use it. That's what is the idea of calculus, trying to approximate. That's how this becomes 2x. Okay, and this becomes 0 and the derivative comes here. Now let's look into the same problem one more time. Okay, the regular way of trying to find the derivatives. So what a derivative means is, as I mentioned, when we are trying to find a slope exactly at each point, and we are not able to find the slope at that point, we are trying to approximate that slope. Now, why are we not able to find the slope at that particular point? Let's say, for in this case of an equation which is linear, for every unit change in x, there is a change in y, and the slope is constant. We know that. Okay, so we need 2 points to find the slope. Here, if I take 2 points, okay, let's just zoom this a little bit, and let's say we have this portion alone. Okay, just to make it very clear, and this portion alone. Okay, this portion alone. Let's say I'm zooming it. Okay, this portion alone, and it becomes maybe it becomes like this. Okay. Just this portion alone. I want to try to find the slope and just zooming it. So I think that this small bit of curve becomes large here. I'm trying to find the slope. I need 2 points. The problem is at these 2 points the slope is different. These 2 points slope is different. So any 2 points I take, it will not be exactly the slope at that particular point. It will have some variation. So what calculus teaches us is when you are not able to find the slope exactly at a particular point, start with the position where you can find a slope, okay, and try to see what happens when it approaches zero, okay, and find a limiting point, which means that you find a point somewhere close to zero, close to the particular point we're trying to find the slope, but stop there, and that is enough to approximate the slope. That's what it means. So we start with, let's take an example of, let's assume that this curve becomes, this curve is actually, a circle, okay, just to see how we are trying to approach this problem. We start here, okay, two different random points, finding the slope of it, then you come here, okay, then you come here. So when you try to narrow down the distance between these 2 points and keep narrowing down and keep approaching this particular point, this slope becomes a tangent. Okay, that is why they call that, okay, if you wanted to find the slope of a continuous curve like this, any point in that slope, the tangent becomes the slope. Try to solve this problem through a regular way. Okay, we are trying to find the derivative of this. Okay, basically the change in y with respect to change in x. That's what we're trying to find. And usually, what we call in calculus is, for us when h approaches zero, the small change we call it as h, and if it approaches zero, what is the corresponding limiting value? Okay, let's use the terminology h tends to zero. I'll show you where this h comes from. So h tends to zero, that is like when the value approaches zero, that is the difference between this point we're trying to find a slope, which is almost having the difference in x to x plus h is zero. That's what it really means. So this x, we have a small increment, that is like we are trying to increment the value of x, that becomes like x plus h, okay, and the whole square if you try to apply it, and this becomes x plus h. Okay, and we are trying to subtract it from the original h, so that is x. This is a change in the value of the value. Okay, the change in value of x with a small increase in h. Okay, and if we try to expand this, it becomes x square plus h square plus 2xh divided by, if you cancel this, it becomes h. Okay, now if we try to we'll try to solve this. Find the derivative of this using another method. This is the method which is normally used. So what it really means is that we are trying to find out what is the value of y for a small change in x. So what is the value of y becomes for a small change in x becomes like x plus h. There is a function f of x. Small change in h, x is called as x plus h. This is a small change, very small change, close to zero. And we are trying to find out the difference between the function with a small change in x with the original function, which means we are trying to find out x plus h the whole square minus f of x, that is x squared. So this is the difference we are trying to find, the rise overall. Okay, we are trying to find the difference. Okay, and this is the rise. Okay, and the run is h. That is h. That is a small change in x. So this becomes, you can write it as dy by dx. That is when h is close to zero. So what it really means is that when the small change approaches zero, that's what it means. The small change approaches zero. The small change into this particular point when it's approaching zero is equal to f plus h, x plus h. It becomes this is, if you apply, what is the function? It's x squared. So this becomes x squared plus h squared plus 2xh. Okay, minus f of x, that is your original function, that is x squared, and divided by the small change, that is h. Now if you kind of cancel these two, this becomes h squared plus 2xh divided by h. Okay, now if you take h outside, this becomes h plus 2x divided by h. Now this h gets cancelled. Now this is where you found a limiting point up to which you can go. Okay, and if you see here, and if you substitute h is equal to 0, finally this equation becomes, when h becomes 0, which means the small change is approaching 0. small change approaching 0, this derivative becomes 2x. If we substitute 0 here, it becomes 2x. That is what you learn as a formula once again. Okay, the derivative of y is equal to x square is 2x. That is because for a small change in the value of x, which we call it as h, how does the function change? Okay, and this is applicable for any values of x. So if x is equal to 1, the slope becomes 2. Okay, sorry, if x is equal to 1, the slope becomes 2. Okay, and if x is equal to 2, it becomes 4. Okay, and x is equal to 3, it becomes 6. Okay, the slope is this is how we should find the slope, and not just way for a continuous graph like this, because it doesn't reflect the exact changes between two units. This reflects. So let's put values like when x is equal to 1, the slope becomes 2. When x is equal to 2, the slope becomes 4. X is equal to 3, the slope becomes 6. So this is the slope of this equation at continuous point interval. This is the derivative. So, and sometimes we get confused. Okay, when you zoom in, how does it become a straight line or a tangent? Okay, when you try to zoom in a circle, how does it become an infinitely small length which you can measure? Okay, and becomes a tangent. So another way to remember a small change is, think about the way with the earth we live in. Okay, this is the earth, right? This is not a flat surface, it is a sphere. Okay, and if you try to believe that it is a sphere, okay, and try to see what happens when you kind of zoom in. Okay, here it is not flat actually. It is a tangent here. Okay, but if you try to zoom in and look into the streets which will be in the roads, the house, this scale does not bend. Okay, it becomes straight line. Okay, if you zoom into the particular point in the earth, okay, and consider that the point where we live, everything is flat. Okay, so it is all the perception that I mean, like, even though things are not flat, and things are continuously changing over the period of time, if you zoom in enough, okay, and we can find places which are flat enough for us to work with. So that is why we're able to put roads, okay, drive cars. Okay, we don't have to think about that we will kind of fall down from a point A to B, you kind of drop down somewhere. Okay, so it's not like, okay, we are going to fall off anywhere. So when we try to zoom in a particular point of a large, infinitely large object, okay, that infinite point becomes a straight line, or you can work with by finding a slope. Okay, and you can work with finding a tangent. Okay, it doesn't have to be it doesn't have to be kind of curvy at that particular point. You can still find out a straight line, and you can still find out a way to work with. Okay, that's how you can, another way, try to recollect the intuition of calculus, that when you zoom in enough, there is still some space for us to work with. Okay, thank you.